Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives, so specifically today we're talking about linear approximation. So let's go ahead and dive into it. Question of the day, what is linear approximation? So if we think about the name, we have linear. Linear means straight line, and approximation means we're going to be estimating something. So answer, we are going to use the tangent line of a function to approximate some value. So let's go ahead and talk about this example with f of x equals x squared. Let's say that I want to take a tangent line at this point right here. That means a tangent line is just going to be the line that skims directly by. The slope of a tangent line is defined by the derivative, and we also use this specific point. So this point is going to be our x1 comma y1, and then the f prime at x1, so the derivative, and we plug in that x value, that is equal to our slope. And then what we use is the equation for a line. We just use y minus y1 equals the slope times x minus x1. So what are we using this for? Let's say I take an x value that's kind of close. We'll take this one right here. What we're doing is we're using the tangent line value. So if I zoom in right here, we're going to use the tangent line value in order to approximate what the actual function value will be. So let's go ahead and see this in action to really understand it. Here we want to approximate f of 1.05 using the function f of x equals x squared at x equals 1. So like we talked about, what we need to do is find the tangent line. So in order to find the tangent line equation, we need to find the first derivative. So f prime of x is equal to 2x. In order to find the slope of our tangent line, m, we want to go ahead and plug in our corresponding x value. So in our case, we're going to plug in 1. So that's equal to 2 times 1, which is equal to 2. So we found our slope. Now, using our equation y minus y1 equals m, the slope, times x minus x1, we want to make sure we have all the pieces that we need. We have our x1 because we know x is equal to 1. We have our slope, but we need to find our corresponding y1. So our y1 is just going to be our function defined at our x value. So that's going to be 1 squared, which is equal to 1. Now that we have all the pieces, we can just go ahead and plug it in. So here we get y minus 1 is equal to the slope times x minus x1. We can go ahead and simplify that outright. I can distribute that 2. So I get 2x minus 2. Go ahead and add 1 to both sides. And so what we're left over with is our equation, y equals 2x minus 1. So our last step is we need to actually approximate the value of 1.05 using the equation that we just got. So here we get y is equal to, and we can plug that in, 2 times 1.05 minus 1. This is equal to 2.10 minus 1, which is equal to 1/10. And so this would be our linear approximation. So let's go ahead and see a more in-depth example of this. So here we have the function, the cube root of x. And first, for part A, we want to find the linear approximation to f of x at x equals 1 and x equals 27. What this is really asking is the equation of the two tangent lines at x equals 1 and x equals 27. So let's go ahead and find those. We, of course, are going to find the first derivative. I suggest we rewrite this because we're going to have to plug in some values to find the slopes. So let's go ahead and write this in a way that's more familiar. So we can drop down that 3 and the x to the 2/3 so that the exponent is positive. And we can rewrite that with cubes if we wanted. So this becomes the cube root of x squared. Okay, so let's work with our two different x values. First, we have x is equal to 1. Let's go ahead and find the corresponding y value. So we have f of 1 is equal to 1 to the 1/3, which this is just equal to 1. And now we can find our slope, and that's going to be by plugging in 1 to the derivative, which that's just equal to 1/3. So now let's go ahead and plug this in to find the equation of our tangent line. So here we get y minus y1 is equal to m times x minus x1. And we can go ahead and simplify this out. So we get 1/3 x minus 1/3. I'm going to go ahead and add over that 1 to both sides. Alrighty, so here we got our first linear approximation equation. So I'm just going to go ahead and highlight that so we don't forget it. Now we need to go ahead and try this for x equals 27. So first, let's go ahead and find the corresponding y value. So f of 27 is equal to the cube root of 27, which this is equal to 3. And now we can go ahead and find our slope. Okay, so here I got a slope of 1 over 27. So now we need to go ahead and plug this into our equation. So we get y minus y1 is equal to m 1 over 27 times x minus x1. So let's go ahead and multiply this out. I'm going to distribute that 1 over 27. And now I can go ahead and add over that 3. So when I add it over, negative 1 plus 3 is positive 2. And so now we have our second equation. I'm going to go ahead and highlight it again because we need to know it. So now that we found the equations for the linear approximation, we can actually approximate some values. So we're going to do that in part B. We're going to use these in part A to determine the cube root of 2 and the cube root of 27. So first, let's go ahead and work with the cube root of 2. Our x value in this case is going to be 2. So we need to use the line that is closest to 2, which is going to be the one where we have x equals 1. So in this case, we're going to go ahead and use y equals 1/3 x plus 2/3. And now what we want to do is just straight up plug in that value. So I get y equals 1/3, and we're going to multiply that by 2 plus 2/3. And here we found our linear approximation. So we get 1.333 about approximately. And so let's go ahead and work with our second one. So here we have the cube root of 26, which tells us our x value is going to be 26. This tells us we're going to have to use a second linear equation. So y equals 1 over 27x plus 2. And that's because that was the x value of 27. So let's go ahead and plug that in and solve. Alrighty, so, calculator. I used my calculator and I got 2.963. So now we have our linear approximations. Let's go on to part C. Are the approximations in part B overestimates or underestimates? So first, let's go ahead and talk about this. When are we going to have overestimates versus underestimates? And that's going to depend on the concavity of the function. So let's pretend we have a function that's concave down, and we want to take the estimate as some random x value. If we found the tangent line or the line of linear approximation, we can see that we're going to have overestimates. So let's say this is our x value. This right here is the actual value, and this right here is the estimate of our value. And as we can see, this right here would be an overestimate. Now, similarly, when it's concave up, I have the smiley face. Let's go ahead and say I want to find the line right here at this point. So it's going to look something like this. Again, let's go ahead and choose a random x value. So right here, this is going to be where the actual function is defined. And below it, we're going to have our estimate. And so since it's below it, this is an underestimate. So what we want to do is we want to look at the concavity of this function. You can either do that by knowing what the graph looks like, but typically in these cases, the point of linear approximation is that the graph is really gross. So what we want to go ahead and do is find the second derivative. So I rewrote the first derivative, and now we can use this to find the second derivative. So I get 1/3 times negative 2/3 x to the negative 5/3. And we can go ahead and multiply that. So I get negative 2 over 9 times x to the negative 5 over 3. So remember, we want to find points of inflection, but the only interval we care about is where the linear approximation is occurring. So remember, we're looking at the points x equals 2 and the point x equals 26. So let's go ahead and think about this when we're finding our points of inflection. In our case, when we set this equal to 0, this doesn't give us any points. But what we do have is an illegal value. So we have an illegal value at x equals 0 because we can't divide by 0. If I were to simplify this equation, I would get negative 2 over 9x to the positive 5/3, which tells us if I plug in 0, I would be dividing by 0, which is illegal. So I don't really care what happens at 0 because my x values are not even less than 0. So I'm going to start at 0 and I'm just going to go off to infinity. So let's go ahead and find a test point. In this case, I'm just going to choose 1 because I think 1 is nice. Remember, we're plugging this into our second derivative. So on this interval, I found a negative value, which tells me it's going to be negative concave down. If you forget what the concavity tells you, you can always just draw a picture. It's really great to make a visual example. So in our case, we could just maybe draw a little tangent line right here. And now I can tell I'm going to be an overestimate, right? So this tells me that the approximations are overestimates. So let's go ahead and actually see what this looks like with the actual graph. So I'm going to zoom in a little bit here. We have our x values that we use to find the actual line. So let's go ahead and start with x equals 1. Our actual line is going to look something like this. It's a tangent line. It just skims it at the point. And now we want to go ahead and talk about our estimated value. So here we have x equals 2, right? And so our actual value is going to be right here when we plug it in. But when we use the line of linear approximation, we can tell right here we're going to have a pretty big overestimation. Now let's go ahead and look at the value x equals 27. This tangent line, or line of linear approximation, is going to be a lot more flat. So it's going to look something like that. And let's look at the x value that we plugged in, which was 26. I mean, I can keep zooming in all I want. I can see it's going to be really close, but it's still going to be a bit of an overestimation because our actual function is going to be that tiny little bit underneath. So that leads us into part D. We want to compute the error in the approximations of part B and which error is greater. Looking at the graph, I think we can make a reasonable estimation, but of course we need to find the actual values. So let's go ahead and plug in what we know. So those were our linear approximations. Let's go ahead and find the actual value. So f of 2 is equal to the cube root of 2, and this, just estimating, is equal to 1.260. Now we're going to do the same thing with 26. So our actual value of 26 is equal to the cube root of 26, which is about 2.962. So in order to find the errors, what we want to do is subtract those two values, but we want to take the absolute value because the error is always going to be a positive value. So when I do that, I'm going to take the absolute value, and it doesn't matter which order you subtract in because we're taking the absolute value. So I'm just going to take 1.333, subtract the actual value, 1.260, and here we get 0.073. So here we have an error. Let's go ahead and find the error at 26. Again, I'm going to go ahead and take the absolute value of our estimation, 2.963, and we'll subtract the actual 2.962. And this is going to be equal to 0.001. So which error is greater? And like we estimated by looking at the graph, the error at 2 is going to be much greater than the error at 26. And the reason for this has to do with the curvature of the graph. As we can see, when x is equal to 1, the graph is a lot more curved than when x is equal to 26, which causes the tangent line to be way more steep at x equals 1 compared to that to x equals 26. So that would be our explanation. Alrighty, so here we have our explanation, and that is our solution. So that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment any questions, topics, or problems you'd like to see done. Thanks for watching.